Okay, in this video, I'm going to cover section 4.9. Okay, so the second. So free mechanical vibration. So so far we have learned the how to solve the second order the coefficient constants and the homogeneous or non-homogeneous differential equations, right? So the now 4.9, so we're gonna return to the chapter 4.1, the mass spring system. Okay, so we apply the methodologies for solving the second order and the constant coefficient, the homogeneous non-homogeneous differential equation to the mass spring system. Okay, so so 4.9. Okay, let's see what happened. All right, so 4.9, so free mechanical vibration. All right, so do you remember that the mass spring system, I mean, the model of the mass spring system, the mass spring system, okay, was my dot prime, right? And then plus the by prime, and then plus the ky is equal to external force, right? So T. Okay, so m is mass, or you can say inertia. Okay, and the v is the damping constant, right? And then k is spring constant. All right, so or the spring constant. Okay, spring. Okay, damping constant. Okay, for spring constant, you can say that the steepness. Okay. All right, so the as what we have done in 4.234, you know, so we're gonna the analyze the motion of the, you know, the object of this model by classifying several cases. Okay, so damped, undamped, free, or force. Okay, I mean free or just non-free, right? So in in the first case, which let's say b equals 0, it means that damping constant is 0. That means the undamped, right? So b equals 0. That means undamped, right? Okay, and also the we assume the external force is 0. It's called free, right? Okay, so then let then what? That spring mass spring system gonna be just my dot prime plus ky, right, is equals 0. Okay, so now this is nothing but what in mathematics, this is the second order, you know, constant coefficient homogeneous differential equations, right? So we know the general solution, the form of the general solution, this one, but okay. But anyway, we're gonna approach this general solution of this one in a view of engineering. Okay. So the first one, yeah, we'll try to solve this. Okay. So since this is a second order differential equation, so I'm gonna uh to make the you know, the coefficient y second derivative is 1. Okay. Then we got this y dot prime plus k over m, and then y equals 0. So now then, let's say the omega is k over m. Okay, it's omega. Okay, all right. Then what? The equation becomes what? Then the equation becomes the y double prime plus omega square, right? Y is equal to 0. Okay. So now we're gonna find out what Ox equation. And the Ox equation is gonna be r squared plus omega squared equals 0. Okay. So then what's the solution? R gonna be, root. What's the root of that Ox equation? Gonna be plus minus what? I times omega, isn't it? Okay. So since this guy has two two complex root. So the form of the general solution of this guy gonna be what? So the general solution, it's gonna be y of t is equal to c1 times e to the alpha t, but alpha is a real part of the complex root, right? Since see in the root of the Ox equation, what doesn't have the real part. So alpha is 0, right? So the exponential term is just gone. The c1 times cosine omega t, the plus c2 times sine omega t. Is it? Okay. And then next one. So, but we're gonna express this one as one single term of sine function. Okay. So this is equal to, we can express this one as a times sine and the omega t plus pi. Okay. How come? How come? So we haven't seen this expression in the online homework. Okay, I gave yeah. So you can search the one of my video explaining. Giving hint about the online homework problem. Then you can see why this is equal to this. Okay, but let me cover again. So how can you get this expression from that one? Okay, so by the way, here a is must be positive. The non-negative. Okay, and then because let's say c1 be a times sine pi. Okay, and c2 is equal to a times cosine. Okay, pi. Right. Then let me see that here. Oh, okay. See that. Then what? Then y of t is going to be a times sine pi, sine c1 a times sine pi, and then what, cosine omega t. Okay, and then plus a times cosine pi times sine, sine omega t. All right. So now this is equal to, that is equal to what? A times sine omega. Oh, there's no. Give me a second. Let me do it again. So this is equal to a times sine omega t, and then plus pi. How come? Well, I use the formula sine a plus b is equal to sine a and then cosine b, then plus cosine a times sine b. Okay. So, okay, so you may wonder that how we can say that C1 is equal to this and the C2 equals this. Keep in mind that C1 and C2 are unknown constants of integration. Okay, so what? there are okay, so then the C1 can be expressed as the expressed in terms of unknown constants, which are a and pi. Okay, can you see that? So we can say that. So now then, this a is called the okay, we prove it. Okay, the a is called what? The amplitude of motion. Okay, amplitude of motion, and the pi is called the phase angle. So pi is called the phase angle. Okay. So now then, but here, all right. So we can express a in terms of C1 and C2. Okay, or so we can express pi phase angle pi in terms of C1 and C2. Okay. So okay, so you may, I mean, let me um figure out the relationship between A and C1, C2 and the pi and C1, C2. So the C1 square plus C2 square is what? This is going to be A square and then sine pi square plus A square and then cosine pi square, is it? So this is equal to A square times sine square and then plus cosine square. Okay, is it? So sine square plus cosine square is what? 1. So we got the A square. It means that A is what? The square root C1 square plus C2 square. I know. So C1 square C2 square is equal to A square, and I take the square root. Then by the square root property, we're gonna get the plus minus sign, right? But you see that? We assume that you see A is greater than or equal to 0. We assume that. Okay. What does that mean? Why we assume that A is greater than or equal to 0? Because we want to set the what uh the sign of y t to be determined by sine wave function. Okay, so A is the only only give us the information about amplitude. Okay, okay, amplitude of motion. Okay, and then this wave function give us the sign and frequency. Okay, so that's why we assume the A is greater than or equal to 0. Okay, so now then, now right here, say is this. Okay, and then next one is C1 is a C1 over A. You see that C, what is it? C1 is A times sine pi. It means that C1 over A is sine pi, right? So C1 over A is equal to sine pi, right? And the C2 over A is equal to cosine pi. Okay, and then sine over cosine, you see that? Sine pi over cosine pi. This is equal to tangent pi, right? This is equal to what? So now we're going to plug in C1 over A into the top and then C2 over A into the bottom. Then we're going to get C1 over C2. Okay. All right. So now, what? All right. So now then, what? Then the sign of C1 and C2. I mean, yeah, the only amount of C1 and C2, or so the sign of C1 and C2 will determine the phase angle pi. Okay. So you see that. So back to the pre-calculus. So it says C1 and C2. Okay. So C1 and C2, all the C1 and both C1 and C2 are positive. Then the what tangent pi must be what between 0 and 9 degree. Does it make sense? Okay. So pi C1 greater than 0 and C2 is greater than 0. Then pi lies in first quadrant. Okay, first quadrant. This is first quadrant, the second quadrant, third quadrant. Okay, and the fourth quadrant. Okay. So what if C1 is greater than 0, but C2 is less than 0? Okay. C1 is greater than 0 and the C2 is less than 0, then pi lies in second quadrant. Okay. Now let me see. And then C1 is less than 0. And then C2 is also less than 0. Then pi is in third quadrant. And then C1 less than 0 and the C2 is greater than 0. Then pi is in first quadrant. So you see that right here. Okay, keep in mind this. All right. So the now let me see. Okay, so now we'll see example. By the way, so here the omega is called the angular frequency. Omega, the square root k over m, that is called the angular frequency. Okay, angular frequency. And then let's see. The natural frequency is omega over 2 pi. That is called the natural frequency. Okay. What's the period then? I mean, look at this. The general solution is 8 times sine omega t plus pi. So the the behavior of the solution, I mean the motion of the object is a sine wave function, right? Okay. So it's vibrating, right? Then it should have the period, right? It should be what? 2 pi over omega, isn't it? Okay. Now then this one. So let me see. Okay. So it's the example. Okay, so this is example 1 in the textbook. Okay, example 1 textbook. So now let's see. Oh, right here. So in let me see. So example 1 is in textbook is this. Let me share the screen. Oh. All right, so we'll see that here. Example 1, 1 over 8. The mass is attached to spring with the stiffness K is 16 Newton per meter. It's depicted in figure 4.1. Let me draw the figure 4.1. Okay, in my sketch paper. The mass is displayed 1/2 meter to the right of the equilibrium point, given an outward velocity of square root 2, and then neglecting any damping or external forces. So you see that neglecting any damping or external forces, it means that the first order, the derivative term is 0 and the external force is 0. Okay, that may be present. Okay, determine the equation of motion of the mass along with its amplitude, period, and then natural frequency. Then how long after release does the mass pass through the equilibrium position? All right, so let's figure out that. So here. Okay, so so let's say, so definitely the object is not hang in the ceiling. Okay, so maybe spring is attached in the wall. Okay, all right. So there is a object right there, and then maybe there's a wheel. Okay, so the spring constant is I mean stiffness. This is stiffness. Okay, all right, and then the inertia is 1/8. Okay, and then the problem says that what? Give me a second. So mass is the mass is displaced 1/2 meter to the right of the equilibrium position. So let's say here, this is the equilibrium position. Okay. Then the problem says that this object is displaced 1/2 to the right of the equilibrium position. So then right there, there's going to be 1/2. Okay. So that's it. That's the actually what? Initial position. Okay. So it means that what? Y of 0 is equal to 1/2. Okay. Does it make sense? A meter, I mean, yeah. So the outward velocity is 2. Outward velocity is 2. Okay. So now outward equals 2 meter per second. It means that what? Y prime 0 is equal to 2. Okay. So we got the initial conditions. This one and this one. These are initial conditions. Okay. So neglecting any damping or external forces. So then and the equation is what? And the second one, I'm sorry, B equals 0, and then external force of T is equal to 0. Okay. So now the question is find the equation of motion. It means that what? Find the Y of T. Okay. Right. So now then, oh, I'm sorry, not Y of T. Find the equation of motion. Sorry. Find the equation of motion. Right. Amplitude, angular, natural frequency, and period. It means that we find out what? We find a solution in terms of the what? The single wave function, sine function, A times sine omega t plus phase angle pi. Okay. All right. And then angular frequency is what? So angular frequency is the omega, which is square root k over m. And the natural frequency is what? Omega over 2 pi. And the period is what? 2 pi over omega. Okay. All right. So now, a second. So this okay here. Let me start with the differential equation. So differential equation gonna be 1/8, right? Y dot prime plus, and then the m. I mean stiffness. Sorry, k. Stiffness is 8, right? 8y is equal to 0. So it means that y dot prime plus 64y is equal to 0, right? Okay. So the angular frequency. Omega is what? Omega is square root of k, which is 8 over 1/8, which is what? Square root of 64, which is 8. Okay, we figure out angular frequency. Okay, and let's find the Ox equation. Is what? R square plus R square is equal to what? Negative 64. So R is plus minus 8 times I. So then general solution Y of t is equal to C1 times cosine AT, right? And the plus C2 times, you see that? C2 times sine AT, which is equal to A times and then sine AT plus phase angle pi. Let's figure out A and phase angle pi. Okay. So now, then what is A? A is the C1. Let's see. A is C1. Right? See, A is a C1. Oh, what happened? Oh, sorry. Sometimes webcam doesn't focus. Oh, yeah. Give me a second. So now, to find out A and phase angle pi, we need to figure out C1 and C2. Okay. So, okay. Let's do that. Yeah, C1 and C2. So how can you find out C1 and C2? Yeah, definitely we have to impose initial conditions. Okay. So now here y of 0, the problem says that y of 0, I mean initial position is 1/2. So C1, what, C1 times cosine 0 plus C2 times sine 0 is 1/2, right? Cosine 0, 0. Okay. So cosine 0, 1. So C1 must be 1/2. Okay. And the y prime dealer. Okay. So and then to impose the the initial velocity, y prime 0 equals 2, we need to find out the derivative of dy of t. Okay. So this is going to be negative a times c1 times sine omega t plus a times c2 times cosine and then at, right? So then we plug in c1 1/2 into c1, right? And then plug in 0 into t. Okay. And then y prime 0 gonna be negative 4 times sine 0, right? And then plus a times c2 times cosine 0. Cosine 0, 1, and then sine 0, 0. So c2 must be 1. I mean, this one must be equal to 2, right? So c2 must be what? 1/4. Okay. Now then, a is what? Since a is the square root of c1 squared plus c2 squared. Okay, so plug in c1, c2, 1/2 and 1/4 into here, the formula. Then we're gonna get the square 5/4. Okay, this is amplitude, right? Okay, and then let's figure out phase angle. Okay, so tangent pi is equal to c1 over c2, right? Which is the 1/2 over 1/4, which is 2. Okay, and then what? Since the C1 is 1/2, which is greater than 0, and the C2 is 1/4, which is greater than 0. So phase angle must be between 0 and pi over 2. Okay. All right. So now then, phase angle pi gonna be arctangent of 2. Okay. This is approximately 1.10715. Okay. Okay. Keep in mind this one must be between what, 0 and pi over 2. Okay, what's the pi? 3.14, So pi over 2, let me see, what's a pi over 2? All right, so give me a second. Uh, yeah, let me figure out pi over 2. Okay, so pi over 2, that's the 1.5707 approximately. That's approximately 1.57079. Okay, so yeah, since this is less than 1.57079, so yeah, okay, yeah, this should be answer. All right. So now next one is, okay, we got, right away, we figured out the general solution, right? So we figured out amplitude and then phase angle, and then we got angular frequency. Last one is what? Natural frequency and period, right? So natural frequency is going to be what? Omega over 2 pi. So omega is what? Omega is 8, right? So 8 over 2 pi, which is a 4 over pi. Then period is going to be pi over 4. Okay, let's see. Now, give me a second. And then, let's see. Oh. So now, give me a second. See. So now let's figure out, I mean, so okay, we figured out all numbers, but let's figure out the graph of the general solution. Okay. So now here, okay. So let me see. Let me draw the coordinate system. Okay. Y. So what we figured out is what y of t is the a is square root 5 over 4. Okay. This is a times sine. Omega is 8, right? So 8t. Okay. And then plus phase angle pi. Okay, pi. Yeah. So 8, this is omega, and this is phase angle, which is approximately 1.10715. Okay. All right, then think about this. When t equals 0, I mean, what at a sine, this sine function gonna be 0 when t is equal to negative pi over 8, right? You see that? So right there, so this is negative pi over omega in general, okay? Then this sine function going to be 0, right? And then t is increasing, then sine function approaching 1, okay? And then the the since the amplitude is not 1 square but square root 5 over 4, so then what this wave function to reach the square root 5 over 4, okay? And then going down, right? Okay, since this function is not involved the exponential function, so the amplitude is just constant. Okay, the amplitude will not be increased or will not be decreased because the exponential function is not involved. Okay, so great, just keep going like this. Okay, so this is a right here. I mean amplitude, and then what's the period? Period is what? This one from here to here. That's going to be period, right? From here to here. So this is, which is 2 pi over omega. Okay, I see. Now then what? And then let me see period right there, and then let me see. All right. Now next one. Now let's figure out this. What? Uh, let's figure out the coordinate. I mean t value at this point. So t is equal to pi. No, t is equal to this. The t is equal to what? 2 pi over omega. I mean, keep in mind, when t is equal to 2 pi, what sine t is equal to 2 pi over omega. Give me me a second. The period, okay. So then let me see. Omega, I mean, sorry, 2 pi over omega minus pi over omega, then we're going to get 0. Does it make sense? Okay. Because, let me see. Omega, then pi, let's see. Yes, right. This is right. Okay. 2 pi omega minus pi omega. Yeah, right. Now the next one, let's see. Now, yeah, I forgot to figure out the question, figure out the answer for the question in the example 1. So how long after release does the mass pass through the equilibrium position? Yeah, I couldn't figure out that, right? So now, second question, okay, let's see. That was question, this was question 1, right? This is question 1, okay? Question 2. Question 2. So how long, excuse me, after release does the mass pass through the equilibrium position? Okay, so then you know what does that mean? So definitely, you know, since we figured out that the behavior of the object is a vibrating, right? So then that object gonna be going force and going just back and forth, right? Okay, so then I think this object going up and then going forward and then backward and forward, backward. Okay, so we need to figure out at what time this object passed the equilibrium position. Okay, you see. So now then, what are you gonna do? So we figured out general solution, right? So now then, we have to, what does that mean? The object passed the equilibrium position. Equilibrium position means that the y of t at equilibrium position, y of t must be 0. Okay, right? So we need to figure out that time t where this guy equals 0. So y of t is what? Let me see. Wait a second. A times. I mean, so give me a second. What's a? A was give me a second. So here a is. Oh, give me a second. I think. Yeah. So yeah, I just. Sorry, but yeah, the problem in the example in textbook says that y prime 0 is a square root 2, not 2. Okay, but yeah. Sorry, but yeah, I got the typo. But it's okay. So let me just keep using the that initial condition. Okay, so y of t is a, which is the square root 5 over 4 times sine, and then at. Okay, let me see. Okay, at plus pi, okay, is equal to 0. Then sine at plus p is equal to pi. Pi is known, okay, is equal to 0, right? So this is going to be satisfied whenever at plus pi is equal to n pi, right? So at plus pi is equal to n pi, right? So the equation, this equation should be true for whenever 8 times t plus pi equals n pi. So what's t? Then t is equal to n pi minus at. Oh, sorry, n pi minus the base angle pi over 8. Okay, that's approximately what? N pi minus base angle pi was 1.10715 over 8. Okay, all right. So but we want to figure out the what? We want to determine the first time t when the object just crosses its equilibrium position. So I'm going to plug in 1 into n. Okay, so putting 1 into n, then t going to be t is going to approximately what? Pi minus 1.10715 over 8. This is approximately, give me a second. So pi minus, okay, 1.10715, okay, and then divide by 8. That's good. That will give us a 0.2543. So 0.2543. Okay, second. Okay. So now we figured out the answer, right? Okay. So now we move to the next case, damped free mass spring system. It means that our damping constant is not equal to 0. Okay, and then but still external force is still 0. Okay, let me cover this one in the next video. Okay, let me stop here because I solved this problem. I thought this problem with the different condition of the outward velocity. So please look at the example 1 in textbook for reviewing. Okay, so any questions, let me know by email, and then let me stop here.